Now that we've introduced the difference between acids and bases, it's time to learn about a measurement system, which is what we call the pH scale, which simply put is used to classify substances based on whether they behave more like acids, in which case we can call them acidic, or whether they behave more like bases, in which case we can call them basic. Now, depending on how acidic or basic a substance is, we can give every substance a numerical rating between 0 to 14, depending on how acidic or basic the substance is. Now, how this scale works, well, in order to understand how the scale works, we need to actually explain why pH is written this way. And pH is written this way because it's actually a short form for what we call power of hydrogen, or power of H+, more accurately. Now, those that remember the acids video will recognize the significance of H+, because whenever an acid is added to water, the water will actually pull the hydrogen off of the acid, causing it to become H+ when the acid is dissolved into water. Simply put, the more acid we add to water, the more H+ is present, and the more acidic the substance becomes. Therefore, we can conclude that pH, simply put, represents the amount of H+ that exists dissolved in water, and therefore allows us to determine how much acid is actually present. Now, logically, one would assume the more acid we have, the more H+ we have, and the higher the pH would be. But this is actually not the case. It's actually the opposite that is true. A low pH, meaning a pH that is less than 7, moving towards the 0 side, is defined as acidic. And what this means chemically is that more H+ is dissolved within whatever the solution is, because the more H+ is present, the more acid was added to the solution, because H+ originates from the acid that releases it. Conversely, this means the more H+ we have, the less OH- we have, and OH- is the opposite ion to H+ that originates from bases. For example, if we take everyone's favorite metal hydroxide base, sodium hydroxide, we can see that hydroxide is here. The less hydroxide there is, the less base there is, and therefore the more acidic our solution will be. In terms of defining bases chemically, it's exactly the opposite. So if we go from 7, and if we have a pH that is greater than 7, moving to the 14 end of the scale, these substances are defined as basic, meaning that more hydroxide is present, because once again, hydroxide originates from bases, so the more hydroxide, the more base there is dissolved in water, and the less H+, the less acid there will be that is dissolved in water. Now, you'll notice with our pH ranges, we specifically defined the acid range as less than 7, not less than or equal to 7, and the base range as being greater than 7, but not greater than or equal to 7. That's because the pH of 7 is our benchmark for determining whether a substance behaves more like an acid or whether a substance behaves more like a base, because a pH of 7 is a substance that neither acts acidically nor acts basically, and therefore we can define the pH of 7 as being a neutral pH, in the same way that an ion charge of 0 is neither a cation nor an anion. And the classic example of a substance that has a pH of exactly 7 is water, because we use water as a benchmark for determining is more H+ dissolved in water or is more OH- dissolved in water. Now, the last question that we need to answer is why the pH system actually uses the numbers 0 to 14, and why a low pH represents more acid while high pH represents more base. Now, the reason for this is the pH scale does not work linearly. Instead, it is what we call a logarithmic scale. Now, in senior math grades, you'll actually learn how logarithmic scales work, but for our purposes, what we can say is that each pH number, rather than being 1 greater, is actually 10 times greater or less than the adjacent pH values. Now, in simple terms, if we compare a pH of 1 to a pH of 2, we see a pH of 1 is closer to 0, which means that a pH of 1 is actually more acidic than a pH of 2, so we can say a pH of 2 is less acidic. Now, if we do 2 minus 1, we see that we get 1. Now, what this means is that a pH of 1 is actually 10 to the exponent 1 times more acidic than a pH of 2, and 10 to the exponent 1 is 10. This is what we say when we say each pH number is tenfold or 10 times different than the pH number that is next to it. So if we compare the pH of 13 and the pH of 12, we know that 13 minus 12 is also 1. We know that a pH of 13 is closer to the basic end than a pH of 12, so this would be more basic. And because 13 minus 12 is 1, we can say that a pH of 13 is 10 to the exponent 1 times more basic than a pH of 12, or simply 10 times more basic than a pH of 12. This gets a little bit more complicated when we have non-adjacent pH values. So if we take a look at these, if we compare stomach acid, which has a pH of 2, and tomato juice, which has a pH of 4, we can do 4 minus 2, which is 2, and because each pH value is a factor of 10 different than the adjacent value, 10 to the exponent 2 is 100. So we can say that because stomach acid is more acidic and its pH difference is 2 numbers different, we can say that stomach acid is 100 times more acidic than tomato juice is. Then if we compare tomato juice to water, water we know is our neutral pH of 7, and tomato juice has a pH of 4, so 7 minus 4 is 3. That's a difference of 3 pH levels between tomato juice and water, and 10 to the exponent 3 is 1,000. So this tells us that tomato juice is 1,000 times more acidic than water because its difference is that of 3 levels of pH. Now, if we go on the basic end, we can compare hand soap and bleach. We can see that bleach has a pH of 12 and hand soap has a pH of 10. 12 minus 10 is 2, and using the pH scale based on base 10, 10 to the exponent 2 is 100. So we can say that because bleach is more basic, because it's closer to 14, bleach is therefore 100 times more basic. Now, because hand soap is our point of comparison, we can say that hand soap is 100 times less basic than bleach is, which again is the same comparison, just going the other way. Now here, if we compare extremes on this end here, we can see that bleach with a pH of 12 and stomach acid with a pH of 2, that's 10 orders of magnitude different. So if we actually write out 10 to the exponent 10, that would be 1 with 10 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this number is 10 billion. So we can say that stomach acid or gastric juice is 10 billion times more acidic than gastric juice. So this tells us how much of a difference the pH scale actually makes, because once again, every level of the pH differs by a factor of 10 rather than working linearly. This concludes our video on the pH scale. In order to understand how to read the pH scale and to make sure that you can determine how much more acidic or basic a substance is, you can take a look at the practice problems at the end of this section here. And once again, your goal is simply to determine if you can figure out whether a substance is more acidic or more basic, and how much more acidic or basic a given substance is.